calculations. 5-ton clump weight were considered on the pipe, 12 numbers with certain spacing in between, and this configuration was followed from our previous experience, where we have connected this a certain kind of concrete weight. The drawing in the right shows that, and followed by the concrete weight of after 65 meters of the pipe length. Some steel stiffening was provided to the pipe for around 30 meters, and the flow inside the since the water is flowing at a very high speed, around 0.2 metric tons per second was considered. So as I said, two cases were considered: normal and extreme conditions. So for the normal condition, the lateral excursion for the shallow water length was around 25 meters, and for the extreme conditions, it went up to around 200 meters. And with that, the effective tension of the pipe also increased to 900 kilonewtons for the normal conditions, and for the extreme conditions, because the pipe there, we observed that there was a bending in the pipe, so the top end effective tension came down to around 700 kilonewtons. And it was also observed that the normal condition had no bending radius problem, but because of the extreme bending in the extreme condition had a huge bending problem, where the bending radius came down to almost 10 meters minimum bending radius. For HDPE pipe, there is a requirement of that the bending should not be lower than 30 times the outer radius of the pipe, outer diameter of the pipe. So clearly, for our case, it is much lower than the prescribed bending. So to address this problem, uh, local stiffening was provided between the concrete weights. Earlier there was only HDPE concrete like that. After that, steel stiffening was provided in between the concrete weights, and the steel stiffening continued up to the chain point. And though there was not much difference in the lateral excursion, but there was a huge difference in the bending radius. The bending radius was found to improve, and it came up to around 30 meters, which was beyond the prescribed. So using the local stiffening, it improved the bending. There was also a study by Hafez et al. In 22, where they have used a continuous concrete coating, and they observed that when they are providing a continuous coating, and when they are increasing the thickness, there was an improvement in the bending radius. In conclusion, I would like to say that we carried out analysis using DNV codes, and as well as the offshore simulation software OrcaFlex, and weights were calculated based on the load combination of waves and currents. And following the weight determination, OrcaFlex software was used to find what are the limiting values for the stresses and the displacement and bending radius. And following the base for the preliminary calculation of considering only the concrete blocks, it was observed that when we are using local stiffening between the concrete blocks, the bending radius problem is going away. Thank you.
Yeah, time for quick one or two questions.
So the water what you're getting, this is as per the distilled water. How do you say the desalinated?
Yeah, sir.
You are condensing the vapor.
Yes,
Right?
sir. Yes, sir.
So its vapor is all pure water.
Yes, sir. Almost the TDS is very low, sir. So we have to remineralize it. Yes.
Are you doing that?
Yes. For this plant, we are doing.
You are hiding those things. You are only releasing only after drilling.
You seem to be interested in the patent of it. You have any conflict of interest? Do you have a company?
How do you create a vacuum? Do you have a pump or how do you create
Yes,
a
sir. We
vacuum?
have a vacuum pump.
You use a vacuum
Yes, sir.
pump. And that is run by what?
Yes, sir.
That you run by what? Diesel generator or
Right now, we are using diesel generator for the LTTD plants. For this one, initial power will be taken from the grid. The grid is run by the diesel generators. So after when we are installing OTEC, so after the initial taking of the power from the grid, when this plant will start producing power, it will give power to itself. So it will not need the grid then, sir.
Ma'am, just an interesting concept that you brought out. However, what is the temperature the brine will be at? 32 degrees or whatever is the seawater temperature?
Mm, the brine will be around, I think, 12 degrees or something. So we have to discharge it accordingly.
Means you have to start the cycle.
Yeah.
So you're taking surface temperature seawater at 28 to 30 degrees.
Yes, sir.
You're creating the differential with 8 degrees deep sea water
Yes, sir.
to create the gradient.
Yes, sir.
But where the vacuum is to be created, where the vapor is to be created, that will be at 32 degrees or 30 degrees, whatever is the surface water temperature.
Hmm.
Or
Yes, sir.
are you giving in more heat?
No, we are not giving any more heat.
So are you looking at a solar panel to pump in more heat to make it more efficient?
No, sir. Actually, the water starts boiling at that temperature itself.
So
Because
how
we
are
are
you starting the
reducing.
vacuum?
Yeah, we are reduced. That's what, sir. We are reducing the vacuum using a pump.
You start the vacuum and thereafter it self-sustains on that
Yes, sir.
itself.
Yes, sir. Yes, sir.
Okay, fine.
Okay, last question from me.
Yes.
So there seem to be some contradictions about your pipeline.
Okay.
It's not being on the bed, being free, but the picture that you showed in which you talk about using the DNV standard to calculate the stability of the pipeline. You show a pipeline on the bed,
This one, sir.
and the CM coefficient that you used, that's 4,
That.
which is
Yeah.
quite high. And usually when the pipeline is almost on the bed, it's about 3.29. Uh, the last bit of my, what I'm trying to understand is, I don't think you included the ocean current, the tidal current anywhere in the analysis.
It,
You seem to have taken the waves. That itself is another big question of discussion, but let's leave that right now. But you don't seem to have taken current at all in the analysis.
it was taken, sir. It was actually Orcaflix has two parts. So we
No, what you have taken, I'm not talking about the software.
Okay, sir.
What,
No, it was considered, sir. Using DNV, you are saying, sir, it was considered.
okay, you didn't mention it in your,
Okay, maybe I missed it
okay.
somehow.
All right, fine, thank you.
Yeah, thank you.
So if you have more questions on this, you can offline because I have been given strict instruction. Thank you, Anuleka. I have been given strict instruction to bring this to a close by 6 o'clock, and we have two more uh, presentations to go. So the next one is a numerical hydrodynamic study of Durpa Sabov. I do not know what that is. In submerged and periscopic depth. It will be presented by Rahul Kumar. Rahul Kumar completed his BSc in shipbuilding repair from IMU Kochi campus in 2019. So he will also bring a lot of energy. Uh, and completed his BTech in Naval Architecture and Ocean Engineering from IMU Visakhapatnam campus in 2021. He did his MTech in Ocean Engineering and Naval Architecture from IIT Kharagpur. Currently, he works as a scientist in Naval Science and Technology Lab. Over to you, Rahul. Keep it to about 13 minutes or so. We can have 2 minutes.
So, thank you for the introduction, sir. Very good evening to all. So my topic for the presentation is numerical hydrodynamic study of DARPA-SABOP in submerged condition and periscopic depth. So, as we know, the 70% of the earth is covered with the ocean region, and which is very important for the underwater oil explorations and oceanography studies, subsea pipelines, and the military services. So it is important to we need to protect the maritime domain so that we can have the quick and proper maneuvering. So for that, it is important to investigate the hydrodynamic coefficient, which is generally describe the maneuverability and the stability of the vessel. So uh, not only on the submerged conditions, the uh, near to free surface is also very important to determine the hydrodynamic coefficient, which is very important for the uh, battery charging and communication with the base and all. So, so there are several methods are available to calculate the hydrodynamic coefficients. Empirical methods, that is inaccurate, and experimental method, that is very costly and time consuming. So recently the CFD is very popular to give the accurate results in this calculation. So what is hydrodynamic coefficient? Hydrodynamic coefficient is nothing but the rate of change of sway force or yaw moment with respect to sway velocity or sway acceleration or yaw velocity or yaw acceleration. I am talking about the horizontal plane stability, and this which is denoted by the YV NV, which is represented nothing but the linear velocity derivative, and YR which is the angular velocity derivative. And these are the hydrodynamics models I used for my calculations. So these are the some literature review I went for the understanding the behavior of the hydrodynamic coefficients, and then I found that these hydrodynamic coefficients is mostly dependent upon the submergence depth. At it is moving close to the free surface or from the seabed towards the mid submergence. So the hydrodynamic coefficient behave differently. So when it is moving from seabed towards the up, this hydrodynamic coefficient is increasing. Pitch and yaw is increasing, and and the pitch and the pitch is almost constant. And also depends upon the length of the bodies. As we change the middle length of the body, the pitching and the heaving coefficient is also varying. And also the stability of the maneuvering stability is also behaving differently with respect to the submergence depth. So as we can see, the submergence depth, the vessel is found to be unstable, and distance of 4.6 of the diameter is found the horizontal plane stability. So objective and methodology. So in this study I used ANSYS Fluent to calculate the hydrodynamic coefficient in submerged condition and near to the free surface in straight ahead and with respect to different drift angle and yaw rate. DARPA is Defense Advanced Research Project Agency, sir. Advanced Research Project Agency.
This is a US based thing.
Yes, sir, US based. Okay, sir. So, for that I generated the offset of the models by using the MATLAB and the Excel software, and importing these offset into the space climb I generated the model, and for generated the mesh I use the ANSYS Fluent, and also for simulating the drags I use the ANSYS Fluent, and I simulated the captive model test and rotating arm test to get the hydrodynamic coefficient and compare these value with the experiment value. So the appended DARPA sub of models, I generated the offset based on the reference givens, and with the model part the main particulars I generated the offset based on the different reason equation is given in the reference. So for the different reasons, the bow parts and the aft body cap, I generated the offset, and I imported into the space climb and rotated about the 360 degree to get the bare hull model, and then I imported the offset of the sail and extruded till the the body, bare hull bodies. And for the Astern's appendage configurations, I use the MATLAB, because by using Excel, these this create the curve is getting the error. It's not properly generating. And this Astern configurations, I generated each 90 degree to generate the plus configuration. So for generating the domain, I use the ITTC guidelines, which is 1.5 length of the model from the inlet and 5L from the outlet and surrounding 2Ls. So for the grid independent studies, I generated the automated mesh based on the local sizings. I given the local sizing on the hull, tail, bow, sail, and appendage and BOI, because these are the reason which is very fine for the drag, and rest other part I given the global sizing. I generated the surface mesh as we can see in the diagrams, and for the volume mesh, I defined the boundaries and the first layer thickness 0.03 mm, and numbers of layer 25 with growth rate of 1.2. And these are the flow parameters I used for my simulations. So Reynolds number, it is coming more than 10 to the power 5, which is behave as a turbulence model. So for this, I use the K omega model, and Y plus value I got around 3. So I generated two set of mesh, which is the very coarse and very fine. So just to know how the drag behavior with respect to the experiment results. So I found that as the finer mesh is giving the more closer result, and the coarse mesh, it is as we are starting with the very coarse, and it got 1 point error of nearly 1. Then I try to increase, then it is error is getting increased. Then I just check with the fine mesh, and I found that this the variation is increases as I am getting more finer. So for my study, for further study of the hydrodynamic coefficient, I selected the 5.4 millions, because although the 3.4 million is giving the accurate results, for just to little bit finer side, I selected the 5.4 million size. And I run the simulation till the 4,500 iteration and near 5,000. And for the doing the grid independent study at the periscopic depth, so the periscopic depth at the model level, I finalized with the average full scale of the periscopic depth and scale down into the model scale, and I generated the free surface plane. And we given the same input as we given in the submerged conditions. In the periscopic depth, only the free surface is given the local sizing to generate the mesh, and for capturing the wave, we given the number of layers near the free surface. So, and these simulations, I give in transient conditions, I selected the time step sizing from 0.001 to 0.05. As it is getting converged, I increases my time step sizing till up to 0.05 seconds. So till 100 seconds, I run my simulations, and then as we can see, the wave is generated. The wave height is from the body axis, it is 7 to 8 centimeter. From the free surface, it is wave height, it is getting around 1 to 2 centimeter. And these I got the drags nearly at 1.5 times what we get in the submerged conditions. So I didn't find much paper to compare the drag. Somehow I found these papers to compare the drag. So with respect to this, I selected the 9.4 million cell grid size for further calculation of hydrodynamic coefficient. So with these selected mesh, I further calculation the aerodynamic coefficient. So for the straight line test, I given the inflow from 0 to 8 degree with the velocity components, and I calculated the x, y force and n moment, and then I non-dimensionalize with respect to using these equations, and uh, I plotted the graph between the non-dimensionalized moment and the sway force with respect to drift angle, and I I did the curve fittings, and the slope of this curve is giving my y v dash and n v dash, which is very much close to the experiment result. And for the rotating arm test, I used UDF to define these my source functions. So for that I selected the R dash based on the facility available in my lab. From then R dash I calculated the omega to simulate the flow, and then I calculated the y force and moment, and then I non-dimensionalized and plotted against the uh, the non-dimensional art and linearized curve fitting did, and then I got the coefficients value. The slope of the given curve will give the coefficient value. So these y dash r and n dash r, it is y dash r is, it is percentage very high because of it is very small numbers. Small change is reflecting so much in percentage difference. So for the straight line test at periscopic depth, so similarly I simulated with the drift angle of 0 to 8 degree, and whatever at a time step I selected, so from 0.001 to 0.05 seconds till the 100 iterations, and then I plotted the the y dash and n dash with respect to drift angles. So these by v dash nv dash, I don't find any paper to compare this periscopic depth result. So as we can say that this coefficient, it should be higher than the submerged conditions, because this is near to the free surface. So in conclusion, we can say that the y dash v and n dash v and n dash r is very close to the experiment result, and y dash r is changing because of it is very small number, and y dash v and n dash v at periscopic depth, it is increasing 10 to 20%, about 10 to 20% in submerged conditions, and also the sway force, it is increasing 1.5 times. For the y dash r and n dash r, we are still developing the algorithm to calculate it at the periscopic depth. So that is our the future scope work. These are the references I follow for my this study. Thank you. Any questions?
Okay, so thank you, Rahul. Uh, because of time, I'll just limit the question to one quick question. Oh, the question can be a bit long, but the answer is to be quick. Okay, any question? Otherwise, you, sorry.
Result or
Yes,
near
sir.
to the experimental value.
Yes,
Still,
sir.
you opt for near to 5 million. Why?
Yes, sir. As I said, so this 3.4 million is giving the 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 closer value. But sir, just for getting the finer size, so I selected the 5.4 million for these, because these with this meshing I'm going to calculate the hydrodynamic coefficients. Like, so because of that only I just selected that 5.4 millions, just to a little bit safer side. Yes, sir, but the percentage is also, sir, not much big. It is only the 1 to 2% in range only. So that is also all fine. I felt error, it can be that much be, that won't be much impact. Thank you.
Okay, thank you. So the last talk for this session is on rudder hydrodynamics in shallow waters, a CFD approach to predictive modeling, and it will be presented by Dr. Jalal. I have a very long bio, but instead of taking your time, I'll just keep it short so that you have more time to present the talk. Dr. Seza Janardhan is Associate Professor and the Head of School of Naval Architecture and Ocean Engineering at the Indian Maritime University, Visakhapatnam campus. She earned a PhD in numerical ship hydrodynamics from the prestigious Indian Institute of Technology, Madras in 2010, marking the beginning of a fruitful academic and professional career that we all witness today in few minutes. Now, so she is a very active contributor to the academic community. She has many years, so I don't like to take the time right now on that. She has many scholarly contributions have garnered significant recognition in the fields of naval architecture and ocean engineering. She was honored with the H.S. Rao Memorial Award for Best Paper for her work titled A CFD Model for Vessel Motion Data Analysis for the year 2023-24, awarded by the Institute of Marine Engineers. She has co-authored many papers. Her award-winning paper, Parametric Studies on the Bulbous Bow to Reduce the Bow-Induced Vortices of a Naval Vessel, co-authored with Dr. Avinash Gode, who is also the co-author of the presentation now. Beyond her research accolades, Dr. Janardhan has played a pivotal role in advancing circular economy initiatives at the Indian Maritime University. So with all that, I invite Dr. Janardhan to take the floor.
Good evening, ladies and gentlemen. It's an honor to be here amongst the leaders and stalwarts in the field. And I thank Frost for giving me this opportunity. So today I'm going to present my little research work on rudder hydrodynamics in shallow waters, a CFD approach to predictive modeling. My co-author, Dr. Avinash Gode, joins me in the audience. And this work is a small part of a project which we have recently grabbed from the Ministry of Port Shipping and Waterways, which has a bigger picture of developing a mathematical model for shallow water maneuvering for inland vessels. This is a small problem that we did as an introductory part of a project. So to give you a brief introduction of what my project is, of course, navigating vessels through restricted channels poses a big challenge because there are augmented forces coming on the hull, propeller, and rudder, along with the moments. And understanding these forces and the interaction between them not only gives a proper prediction of maneuverability, but also they give a good fuel efficiency, which is very important. If I recall the words from the chief guest today this morning, Professor Gokaran, he did mention that green technology doesn't come necessarily from renewable energies on the board. It also comes from tweaking the existing system a bit, and this is what we have chosen to do in this project. This is a step towards a green and sustainable approach in shipping. So rudder behaves in a different way in shallow water. If you recall the presentation from the keynote speaker, Professor O.P. Shah, he did show us a turning circle maneuver in shallow water. So rudder has a bigger contribution to controllability, and often the hydrodynamics of rudder is neglected and we concentrate mostly on hull. And unless it's very shallow water, hull derivatives are never dependent on any other factors. Unless it is for very high velocities and very shallow water depths, hull derivatives are always dependent only on the principal parameters and the shape. So, but we do concentrate a lot